So good morning, everyone. I warmly welcome you to another lecture of ME 324 Finite Element Analysis. And today, of course, we will be focusing on, in the first part, we focus on different techniques used for numerical integration before we move on to discuss 3D problems, 3D finite element issues, let's say, elements, 3D elements, which can be used to model 3D systems which are subjected to three-dimensional stresses. So why we need to discuss this numerical integration scheme is, you saw in the previous lesson, we used an isoparametric formulation, meaning without using a global coordinate system, we used a natural coordinate system to derive the stiffness matrix for, let's say, higher order elements and with higher dimensional elements. There we already saw that when we wanted to obtain the stiffness matrix, we needed to perform an integration over certain boundaries in order to calculate the stiffness matrix for these elements. So we already discussed that by moving from the global coordinate system to a natural coordinate system, the integration becomes quite easy because it is bounded by a certain domain. And also, on the other hand, it is quite easy when it comes to implementing in a software. So today, within today's lesson, let's see what are the numerical techniques which are commonly used in finite element methods, and how they are like actually implemented, and what is the working mechanism, or what is the how these integration techniques calculate the or perform this required integration using of course numerical technique. Most of the things which we will be covering today you might be probably already know, either in form of different names, but for completion's sake I will just mention these numerical techniques so that you know what are the numerical techniques which are applied or implemented in the computer software or the computer program which are using for finite element simulations. And then we will move on to discuss 3D elements, a tetrahedral element for modeling 3D stresses, and of course let's see how isometric parameter formulation can be used to derive a hexahedral element for modeling 3D elements. So you may now realize that we increase the complexity of the element either by increasing the number of nodes or using higher order shape functions. So you see, we need the help of the computer to solve these complex problems, but you need to have an understanding about how these systems are implemented in a computer or implemented in the software. So on that note, let's start with these numerical integration techniques which are used in finite element simulations. So when we talk about numerical integration techniques, we can think of two main techniques which are commonly applied in finite element simulations: the Gaussian technique and the Newton-Cotes quadrature technique. So Gaussian quadrature, first let's discuss the Gaussian quadrature technique. So we use this technique, of course, to perform to evaluate an integral in a numerical sense. So assume that we are required to evaluate an integral bounded by -1 to +1. If we think in terms of an isoparametric formulation, assume that we are required to evaluate this integral. So here we consider y is equal to yx, so it's a function of x. In order to evaluate this function, we need to select the value at a certain point, a certain y value for a particular x value, and then we need to perform a calculation of area. So it would be straightforward if I just draw the corresponding curve, so to say, right? So assume you are given a function. Assume your y function, the given y function, which is to be integrated. Let's say y is equal to, this is given by, required to evaluate this integral from -1 to +1. In simple terms, you need to evaluate the area under this curve. Yeah. So in this numerical technique, in this Gaussian quadrature technique, what we do is we select, in the case of 1-point Gaussian quadrature, we select only one particular point, meaning we select a midpoint, this point, let's say, where the corresponding y value, the corresponding value of y, where x is 0. Yeah. So we can assume this to be y1. Okay. Then what we do is, we once we select once we select a midpoint of this curve, we then simply multiply by the length of the interval of the integration domain. So if we assume this at 0, y0 is equal to y1, we try to, what we do is calculate this area, and we assume it to be approximately we assume it to approximate the area intercepted by the curve. So if you use 1-point Gaussian quadrature integration technique, we select one particular point, the midpoint, and we call it y0, and simply, so this is the height, then we simply multiply it by the integration length of the interval. In this case, it is 2. So we can approximate this. We are interested in evaluating this integral of yx dx from -1 to +1. And in this 1-point Gaussian quadrature method, we assume that it is approximately equal to y0 times the length of the integration interval. So this is quite familiar, I guess, for you all. We also call this a midpoint rule. You may have already used this to approximately calculate the area intercepted by certain curves. The first approximation, call it a midpoint rule. So if we try to generalize this, and in this case, of course, we used only 1 point. If we think of like many number of points, we can write a general form for this equation. We can write I is equal to integration from -1 to +1 yx dx. And what we do is we select certain points and we multiply each point with a certain weight factor, and we calculate the area over all the number of, let's say, number of elements that we have considered. What we try to do is, in other words, we try to evaluate a function at several sampling points, n number of sampling points, by multiplying each value, let's say yi, by an appropriate weight factor. And what we do is we add all the areas together. Since the Gauss method chooses the sampling points, so that for a particular given number of points, this method is possibly more accurate than the Newton's Cotes quadrature method, where the sampling points are decided by symmetry, or you take equally distant sampling points in the Newton Cotes quadrature method, which we will see. But in this case, in the Gaussian method itself decides where the points should be located. So to get a more idea as to how this method can be applied, let's now consider a 2-point Gaussian formula. just to get before we generalize this. So the general formula is, I will write it again. Yeah, right. So the general formula that which we will be using in this Gaussian point integration scheme is that any function we are interested in evaluating the integral of a certain function bounded by -1 to +1, which can be approximated in numerical sense. So you know why we need to approximate it, isn't it? Because if this yx function is not exactly described by a polynomial term, let's say polynomial, given in the function of, let's say, 2n-1 or less, we cannot perform an exact integration for this particular function. So in that case, we need to discretize it and evaluate the integral in the form of using numerical techniques. So what we do is, so by the summation sign, what we mean is we try to add different segments. So we add them, try to evaluate them numerically where certain points are selected, and the value of that particular point is weighted by a certain weight factor summed over all the number of intervals which we are interested in. If we think of a 2-point Gaussian quadrature integral, I think this will be quite clear to you then when we discuss the 2-point Gaussian quadrature. This is the function we are interested in. We are interested in calculating +1 and -1. And what we do in this case is we select certain points. Of course, the Gaussian method itself select a particular point where we need to evaluate the function or obtain the y value of the function. We will see it in a short while. So for a given x1 value, the corresponding y1 value will be used. For a given x2 value, the corresponding y2 value will be used. And then we can apply this equation which I have written here to evaluate the integral of the curve bounded by -1 to +1. Shortly, right? Number of points to be considered in the integration scheme, and based on the number of points, there are certain locations we have to select over x values, and of course we need to also write down what are the associated weights. Let's call them wi's. So if we have a single point, just like in the previous, the first case which we discussed, if we have only one point with the Newton's quadrature method, and we apply, then the location of the corresponding x value we have to use is x1, since we have only 1 point, is 0. The corresponding weight factor is 2, if you can remember. Corresponding weight factor is 2. 2, you can see 2 is multiplied by y, that's 0. So x1 corresponds to 0, and the weight factor is 2. Likewise, for if there are two points, just like in this case, the case which we have just have drawn here, of course, there are 2 points to be evaluated. Then there are 2 points where the y value should be evaluated. What are these 2 points? Let's call it x1 and x2. These corresponds to plus or minus 0.57735. Likewise, so this method has been published. We will have to use these values. We will shortly see how these values are obtained. Okay, don't worry. the method behind obtaining this value. So each of these evaluated values, the yi values, has to be multiplied by the weight factor 1. Similarly, if there are 3 points, we have to evaluate the y values at 3 locations. The x1 and x3 corresponds to plus or minus 0.77459, and x2 value should be evaluated at the midpoint, I mean the very center, and the corresponding weightage factors for x1 and x3 should be equal to 5 divided by 9, and for x2 should be 8 by 9. So likewise, when you have 4 points, then there are another locations as 4 locations, and also corresponding weight factors based on this Gaussian quadrature method for evaluating, numerically evaluating the integration, numerically mimicking, let's say, when we want to evaluate an integral or to perform a numerical integration. So if we consider the 2-point Gaussian quadrature method, where n is equal to 2, we can write down the integral which we like to evaluate, which is y times dx, evaluated from -1 to +1. Since we have 2 points, we know we have to evaluate the curve, the function at 2 points, y1 and y2. And we know we have to multiply each value evaluated by a certain weight factor, and of course add them. Yeah. So if we can rewrite them again, y value has to be evaluated at x1, and at y another value has to be evaluated at x2. So since you know, you can see there are 4 unknowns. Yeah. W1, W2 is not known, x1 is not known, and x2 is not known. So since there are 4 unknowns, let's assume a cubic function for y according to the following way. We can assume y to be equal, let's say C naught, assume a cubic function to represent y. What we are trying to, what we are interested now is to calculate the area, isn't it? By calculating the integral, we are aiming like to perform, by performing an integration within this domain, we plan to our aim is to calculate the area. So the y value is 0 plus c1x, c2x squared, and c3x cube, which we like to integrate. And this is simple integration. After doing the simple integration and substituting the upper and lower boundaries and evaluating the integral, what you would end up is getting, you can try it on your own. The other terms will cancel out, only C naught term and the C2 term will be remaining in this as a solution of this integral. We already have obtained, let's say, a value, let's say, for the area by assuming a cubic function for y or for the curve. So in order to apply this method, let us also further simplify this problem. That is, let's assume a symmetry where, let's say, the weight factors are equal, and of course the corresponding x values are same in magnitude. If we use symmetry, this is, I mean, this is a special case. If we assume it, use symmetrical located points, then the Gaussian formula, let's say, let's call it the area given by the Gaussian method. Simplicity, we know the weight factor. Now W1 is equal to, okay, before that maybe I should write. So let's say W1, the weight factor is equal to W2, which is equal to W, and the X1 is equal to X2, of course, the opposite sign, where X can be either plus or minus A, according to, let's try to simplify it this way. So what is given by the Gaussian method would be weight factor multiplied by the corresponding Y value evaluated at minus A, weight factor, the corresponding Y value evaluated at plus A. So if we substitute these A values, of course, in this equation, which we just wrote down at 7.4.4, what you would end up is getting 2W C0 plus C2 A squared. We simply substitute the value for this equation 7.4.4. What is the error, right? When we want to evaluate the integral, let's try to evaluate the error given by the Gaussian method and the exact integral which we like to calculate. So the error is what we are interested at. So we are trying to minimize the error in this method. So let's call the error E is equal to the area given by the exact integral which we like to evaluate by equation 7.4.5 minus the area predicted by or given by the Gaussian method. Our attempt is now to minimize this error, isn't it? We would like to minimize this error. For this, we just do a optimization method. How we would like to minimize this error such that we get the minimum error, so that we know in this function we have two variables, those two constants, of course. In this case, of course, variables, because it decides the value of the A values as well as where the X value is located, as well as we are interested in calculating the weight factors, isn't it? This is the whole intention of performing this integral. What we can do in this case is, since A is a function of C0 and C2, we would like to calculate these weights, and whereas we would like to obtain values of C0 and C2 so that the error is minimum. For that, what we can, the condition which has to be satisfied is the partial derivation with respect to C0 should be equal to 0. So what we do is we take this error function and differentiate it with C0. What you would obtain is since of course when you differentiate the first function with C0, you would get up only value of 2, others cancel out, others become 0. In the second case also, you will only get 2 times W. So it would be 2 minus 2 times W. 2 minus 2 times W is equal to 0, where W is equal to 1. Let me just for the simpleness. Right. So what is the other criteria which we need to use? We are now also interested in minimizing the error with respect to the C2 value. What we do is we obtain the partial derivation for this error function, which is A minus AG, and see what is the result that we obtain. If we do the differentiation correctly, what you would get is 3 by 2 minus 2A squared W. Since W is equal to 1, this equation now will give us the value for A. This corresponding X1 and X2 values is equal to square root of 3, which is nothing but 0.7773. So what is the result that we have obtained? The weight factor which has to be used is 1, and the corresponding values, the points which we need to select for evaluating the integral is located at 0.5 0.5773 plus or minus values. This is exactly what you have, what you would also see if you look at the published results. The corresponding weight factors are 1, and the points we are the locations of the x values, which is decided by the Gaussian method, which gives the minimum error, is plus or minus square root of 1/3, or in other words 0.5773, so on. So this is the method which is applied for this, or this is the values which we see. We get the same values when we use the Gaussian. When we we see why we have got these values as such, I mentioned in the table for this Gaussian quadrature method, 2-point Gaussian quadrature method. You know the rationale behind arriving at these weights as well as locations. So in order to get familiarized, let's say with this method again, let's try to do an example. I will also give you some few minutes to work out this on your own. So let's try to evaluate, let's say, two integrals using this Gaussian quadrature method. Let's apply 3-point Gaussian quadrature method. I have given already the values. The first integral that we are interested in evaluating is squared cos x divided by 2 dx, and we are interested in calculating the integral from -1 to +1. So use Gaussian 3-point Gaussian quadrature. Okay, and I will give you now the corresponding weightage factors. So it's simply x squared plus cos x divided by 2, which has to be integrated between -1 to +1. And these are the values corresponding to 3-point Gaussian quadrature when you would like to apply 3-point Gaussian quadrature method. The corresponding x values and where the function has to be evaluated, and the weighted factors. Just give it a try. x1 and x3 should be plus or minus 0.77459. The x2 value, which is at the very center, corresponds to 0. And the respective weight factors, which has to be multiplied with the y1 and y3 values, are 5/9. And the weight factor where the y2 value, which has to be multiplied, is 8/9. So what we can do is we can use the values given in the table. I will write it down here again. So what we are interested is to evaluate the area or evaluate the integral. So we are supposed to use 3-point Gaussian, quadrature method. So meaning there are 3 points where we need to evaluate the function. What are the 3 points? We need to evaluate a function at x1 and x2 as well as x3. The value at x1 and x2 is plus or minus, depending on, of course, which value you take, 0.77459. x2 value corresponds to 0, and then these values have to be multiplied by the weight factors. So W1 and W3 is equal to 5/9 according to the table which we have there, where the results have been published already, which gives the minimum error. So then the integral simply becomes, I will skip some certain steps and write it down. So x squared, that is, let's select x1 first of all, meaning minus 7.7759 squared plus cos minus 7.77459 divided by 2, of course radians, multiplied by the x1 should be multiplied by 5/9, and the x2 value is nothing but 0 squared plus cos 0 divided by 2, and x2 should be multiplied by 8/9. And the third term, x3, once you substitute into the equation, it's plus 0.77459 squared plus cos 0.77459 divided by 2, which has to be multiplied by 5/9, since the corresponding weight factor for x3 is W3, which is 5/9. So if you evaluate this formula, what you would end up is getting, according to 4 significant figures, you would get 2.585. We have, compared to the exact solution, we have, let's say, if we evaluate this integral, this is a straightforward integral where the exact integration is possible. And if you evaluate this exact integral, you would get the same result. In this particular example, the 3-point Gaussian method and the exact integral use the same results up to 4 significant points, which is quite nice to see. Yeah. So this is also one of the sole reasons this Gaussian method is commonly used in finite element simulations. This seems to be more accurate than the Newton's quadrature method.